The New Age of Measurement, a story of the SI units. In the heart of science and technology lies a quiet, invisible framework that holds our understanding of the universe together, the International System of Units, or simply SI units. These are the 7 fundamental measures that define how we quantify the world: length, mass, time, electric current, temperature, amount of substance, and luminous intensity. For centuries, these units guided our progress, helping us build bridges, design rockets, decode atoms, and understand life itself. But the way we defined them had to evolve. Once, the meter was a metal rod in Paris. The kilogram was a platinum-iridium cylinder locked away in a vault. The second was tied to the rotation of the Earth. These were practical for their time, but fragile and limited. What if the kilogram lost a few atoms? What if the Earth's spin changed? The world of measurement needed something better, something unchanging and eternal. So, in 2019, science entered a new era. The definitions of the SI units were rewritten, no longer based on physical objects or changing phenomena, but anchored to the unchanging constants of nature, the deep rules of the universe itself. The meter, for instance, was redefined in terms of light. Instead of relying on a physical object, scientists defined 1 meter as the distance light travels in a vacuum in 1/299/792 for 58 of a second. This change meant that any lab on Earth, with the right equipment, could realize the same standard precisely and reliably. The second, already based on atomic time, became even more exact. It was defined as the duration of 9,192,631,770 oscillations of radiation emitted by a cesium-133 atom, time, measured at the quantum level, giving rise to ultra-accurate atomic clocks. But the greatest leap was for the kilogram. For over a century, it was defined by a single object, a metal prototype. If it changed even slightly, so did the world standard for mass. That changed forever when scientists tied the kilogram to the Planck constant, h, a fundamental constant in quantum mechanics. Now, the kilogram is defined using advanced instruments like the Kibble balance, which links mass to energy and frequency through quantum theory. The ampere, the unit of electric current, was once defined by the force between wires. Now, it is tied directly to the elementary charge, E, the charge of a single electron. With this shift, electric current is defined through the number of electrons flowing per second, connecting electronics and physics more tightly than ever. Temperature, too, gained precision. The Kelvin, once based on water's triple point, is now defined via the Boltzmann constant, K, which relates temperature to energy at the molecular level. It allowed scientists to define temperature in any setting, not just relative to water. The mole, used by chemists to count particles, no longer depends on the mass of carbon. Instead, it's based on the Avogadro constant, exactly 6.0221407 times 10 superscript 2 superscript 3 particles per mole, a fixed count, like stars in a precisely mapped sky. And finally, the candela, the unit of luminous intensity, remains linked to human perception, but its definition is now rooted in the luminous efficacy of specific monochromatic light. Ensuring consistency in how we measure brightness. It is now defined based on a source emitting light at a frequency of 540 times 10 superscript 1 superscript 2 Hz with a specific radiant intensity. This definition connects brightness to measurable energy output. Together, these redefined units now speak a language of fundamental physics. No longer dependent on fallible objects, they rely on constants of nature, the speed of light, Planck's constant, atomic frequencies, and the energy of particles. This makes our system of measurement not only more accurate, but universal, the same whether you're in Paris, Tokyo, on the moon, or someday on Mars. This great transformation marked a rare moment in history, a triumph not just of physics, but of human collaboration, precision, and vision. The SI units are no longer guardians of the past. They are now built for the future, ready to support science, technology, and innovation for generations to come.